Well, good evening. This is my first time up on this particular mesa. I've lived in Carlsbad now for about 3 years, and typically about all I see of this part of the world is bumper to bumper freeway. So I really haven't been able to explore some of these areas very much. But I was telling Don, Siri directed me off of Balboa through the big neighborhood to the north of here, I guess. And I thought, does she know where I'm going? And turn right, turn left, turn right, turn left. And I make this one right turn, and it looks like a castle on the hill. And that was one of these buildings here. I was really impressed. I was not expecting a place this big. So anyway, so most of my career in terms of teaching and research while at Northern Arizona University was spent studying sedimentary rocks. I think I can probably brag that I probably studied every formation on the Colorado Plateau, at least a little bit, some to a great extent. And there's a lot of formations on the Colorado Plateau. Just think of the Grand Canyon with all the rock units there. So that's where I spent most of my academic career. And then I started really getting fascinated. I've always been a student of Earth history. And I started getting very, very interested in what the Earth looked like at times in the past, just wishing there was a time machine that would take me back somehow. So I used to draw with just pen and ink. I don't think anybody uses pen and ink anymore. But you use a crow quill pen and you make fine little drawings to show shorelines and rivers and this and that. And that's how I got started. And then along comes Photoshop. And Photoshop, if you're into that kind of thing, it's just the most amazing thing ever. You can do so many things with it. And so I've learned over the years to make maps that actually look like you're in a satellite 200 million years ago, or 500 million years ago, or 300 million years ago, or 192 million years ago, or whatever. So anyway, that's what I've been doing mostly for about the last 25 years. And so, without further ado, let's get started here. If I can remember the system, there we go. So I'm going to do this talk basically in two parts. The first part is actually fairly brief. I'm going to talk a little bit about how I make some of these maps, the techniques, and so forth. And then for the second part, we're going to do some Earth history. And I decided for this part of the world, let's look at the last about 150 million years of time that influenced Southern California and the surrounding areas. So we'll start with the Cretaceous and then go through the Cenozoic. One of the things I want to emphasize is what makes the geology here both complicated and interesting is that the nature of the boundary between Western North America and the ocean to the west, which of course today is the Pacific Ocean. It wasn't always the Pacific Ocean, but there's always been an ocean, almost always been an ocean to the west. The nature of that boundary over the last 150 million years has changed quite dramatically. And I'll define some of these terms a little bit later as we move along. I know some of you are fairly familiar with geologic jargon, and some of you probably not so much. So during parts of the Cretaceous, the area was subjected to what we call normal subduction, where an ocean plate is subducting under the western part of the continent at a fairly normal angle. What does a normal angle mean? About 45 degrees. So the Pacific plate, or back then it was actually called the Farallon plate, was subducting under North America for a very long period of time. And then in the later part of the Cretaceous, the angle of subduction rather suddenly, geologically speaking, rather suddenly changed from about 45 degrees to maybe 10 or 15 degrees. And this wreaks havoc with the system, because normal subduction moves pretty smoothly at this 45-degree angle. But as soon as you either oversteepen it or flatten it, something else is going to happen. And that happened at the end of the Cretaceous. And after that was established, a complete new change in the boundary took place in the, about 35 million years or so ago. And this is when the East Pacific Rise, which is the big spreading center in the central and southern Pacific Ocean, goes all the way almost down to Antarctica. This big spreading center started to intercept Western North America. And what that did is it changed Western North America from a subduction margin to what we call a transform margin. And again, I'll explain some of these things as we move along. So those are going to be some of the take-home messages out of this talk: is normal subduction, shallow subduction, and transform margins. I'll take you through these steps. Okay, so let's look at some of the ways that I make, or some of the data and things that I use to make these maps. Like I say, I use the program Photoshop, and I'll show you, rather than read this list to you here, I'll show you some examples here. This is an example of a fairly simple paleogeographic, paleotectonic map at about 32 million years ago. It was done by a professor at UC Santa Barbara by the name of Tanya Atwater, and she's an expert on what happened to Western North America during about the last 40 million years or so ago. So this is one of the maps out of her, is actually a movie that she's made. This is one of the frames out of that movie. So I can take this information and get a start on what the paleogeography of Western North America would have been like. So it's one piece of information. It's one piece of the puzzle. Another really complicated puzzle we have to deal with is, perhaps you've heard that much of Western North America is made of terrains, of blocks, bigger blocks of terrain, many of which came from other places. Some which may have come from as far away as China or Alaska or South America. And these terrains collided with Western North America primarily beginning about 200 million years ago, continuing to about 40 or 50 million years ago. And all this map shows, you don't have to worry about the details, but all this map shows is where these terrain, all these abbreviations are for the various terrains. And then I took this area here, which is the Southwest, and blew it up a little bit. So we're sitting right about, let's see if I can get my bearing here. We're sitting right about in here. Whoops, right about in here. And so we'll talk a little bit about these terrains, but that's not the major part of this talk, and that's best for another talk at another time. One of the tools I use, most of the states have their geologic maps online digitally. Almost any state, you can go to their geologic survey and you can find their digital geologic map online. And this is the California digital map. It's reasonably detailed. If you had the paper copy, it would go almost, but not quite, from floor to ceiling. It's a pretty good sized map. So I can take this map now, because it's in digital format, and I can carve it up. I can carve it up and move pieces around, and I can move these pieces around to match what we think, or where we think these various blocks were, in this case, about 15 or 16 million years ago. So we see San Diego, for example, sitting way down here, south of Desert Center, rather than Desert Center is on I-10, just the other side of Indio, if you don't know exactly where it is. So it was way south of Desert Center rather than its present location up here. So San Diego's way down here. San Luis Obispo is much further south than it is today, and so forth. So I could carve these pieces up. The other thing I can do is I can use the information on this map to tell what geologic units were present and where and when. For example, we're showing the Miocene here. So again, 15, 16 million years ago. So what I did was, the Miocene pattern is kind of this mustard. I know there's several yellows in here, but one of these mustard yellows is the Miocene. There's a lot of Miocene rocks through central and southern California. And so I see where these units are. And the other thing that you can't see on this map is there's actually a different symbol for Miocene rocks that were deposited in a continental environment versus those that were deposited in a marine environment. So you can, if you look at the digital map and blow it up, you can actually see this. So I can take this information then, and I can make a very simplistic map showing the distribution of land, of areas where continental deposits are being formed, and where marine deposits are. Again, here's San Diego down here. It belongs today, of course, way up here. So this is a piece of information I can use. So the point I'm trying to make is I can use different pieces of information, put them together, come up with a simplified tectonic and paleogeographic map that shows, in this case, the volcanics are in this sort of soft brownish orange color. Higher elevations are in browns, and the lower elevations are in the paler browns and yellows. And we get this information, again, from a number of sources in the geologic literature. Okay, I didn't just sit down and make this thing up. I used all kinds of data to get this far. Well, this still is not the kind of paleogeographic map that I call a finished map, but this is getting me well on my way to doing it. And so lo and behold, I take all this information plus other information. There's information in the Miocene of the elevation of various parts of California and Nevada and so forth. There's information on where the rivers were. There's information on how deep the water was that these rocks were deposited in and so forth. And so finally then I can come up with a paleogeographic map that, and again, just for reference here, there's San Diego in the Miocene, and here's San Diego where it belongs today. And we'll talk about how it got from point A to point B there as we move along. Okay, this is, actually I'm going to skip this map. All I want to say about it is that geologists could take various pieces of the landscape and reconstruct where they were at various times. We give that the fancy name of Palin spastic restoration. This is just an example of about, let's say, 125 to 175 million years ago of where some of the pieces that make up Western North America were located then. Okay. This is another kind of Palin spastic map that some geologists up at Caltech put together a series of maps from about 36 million years ago to present at about 2 million year intervals. And they showed how the various blocks that make up Western North America moved through time. To do this, they had to understand every single fault in the western US and which way it moved and how far it moved and so forth. Again, it may not quite be rocket science, although they're from Caltech, so maybe it is, I don't know. But anyway, when you look at these two maps that are, what are they, 10, 14 million years apart, you can see the, this block here has rotated and moved. This long, narrow block here is further south here and further north here and so forth. So anyway, they've done this in great detail. So now I know how the various blocks of landscape have moved through time over the last at least 36 million years. Okay? Then what I can do is put paint, if you wish, on my maps. And I do this with a marvelous program, or actually it's not a program, it's a site called geomapapp.com. Oh, I'm sorry, you know it's not .com, I'm pretty sure it's .org. Ooh, I think that's, anyway, if you just put Geomap app into Google, you'll come up with it. It's quite a site. It's got NASA and NOAA data, and they have all these digital elevation module maps of the whole world. And so I can take a chunk. In this case, I took a chunk of, this is a mountain range in Spain. So this is what it looks like in Geomap app after I've fiddled around with it a little bit. And then I can paint that. I can take the cloning tool in Photoshop and paint that on one of my maps where I think that kind of a mountain range existed in the past. So I actually clone the information off of, in other words, when you see my maps, I didn't draw each and every one of those mountain ranges. I cloned them from modern digital elevation modules. So anyway. Okay, just a quick look at the time scale. Most of you probably are at least somewhat familiar with it. What we're going to do is we're going to focus on about the last 145, 150 million years through the Cretaceous, the Paleogene and the Neogene, and the Paleogene and Neogene have been broken up into the Paleocene, Eocene, Oligocene, Miocene, Pliocene, and then the Quaternary, which includes the Pleistocene and where we are today, the Holocene. And these are the ages of the boundaries of each of these boundaries in millions of years. MA means mega annum, or millions of years ago. Millions of years ago. So when you see 7.5 MA, that means 7.5 million years ago. Okay? That's pretty standard in the geologic way of doing things. Okay, so let's get on then to part two, and let's look at the geologic history of particularly our part of the world. I'll stray a little bit and talk about a few other things now and then, but we're going to focus on this part of the world. Most of these maps now, you're going to see a good point to focus in is this Four Corners area where Utah, Arizona, New Mexico, and Colorado come together, the Nevada state line, the Nevada-California line. And so you'll see, and if you, at least those of you closer up can probably see the county lines as well. So I use these to pinpoint the location of various geologic features. So, okay, so in the Jurassic, the subduction was taking place along western North America, but offshore were a whole series of island arcs. And if you ask 10 different geologists how many island arcs were there and where were they located and which way were they subducting or whatever, you'd get 10 different answers. It's a very complicated period of time. The rocks are now so bungled up, so messed up, that restoring them is very, very difficult. So even the best of geologists that are looking at the same set of data will come up with different interpretations because it's so complicated. So anyway, this is my interpretation, not necessarily better than anybody else's, although it matches several of the published interpretations out there, showing each one of these is a string of island arcs. This would be very much like the area today to the north and east of Australia. There's a whole series of arcs out there, the Banda Arc and the, what are some of the other ones out there? Anyway, there's a bunch of arcs out there in the South Pacific. And many of them are in the process of either colliding with Australia or with Southeast Asia. And so that's what we think the Jurassic may have looked like. Eventually, these arcs collided, and when they did, they produced a major mountain building event. Geologists use the word origin or orogeny for mountain building. That's what the word means. So this has been named the Nevadan orogeny, actually named after the Sierra Nevada. And it was when all these arcs collided with Western North America, and then that reestablished a new subduction zone along the coast here. So this is our first setting. Remember I said I'm going to take you through 3 plate settings? Actually, this is the one before was just background. So here's the first one we want to discuss today. Okay. So here's this subduction zone running the length of the coast. The arcs are forming starting to form in this region through here. This area will become the Sierra Nevada. This area here is a marine basin in which sedimentary rocks were being deposited. This is the trench right here in which sediment was being deposited and deformed and so forth. And so what we want to do is we want to look at these various components and try to figure out how they behave through time to establish, in order to establish our geologic history. So we're still in the early Cretaceous here, of roughly 105, 110 million years ago. And we still see then this subduction zone running almost the length of the Americas. In fact, this probably connected with subduction down in South America and then ran up all the way up to subduction in both Alaska and Siberia. So that would be very shallow marine seas down here in southern Arizona and across Texas, and then along the coast here. And again, for reference, there's the 4 corners. So there's Arizona, Utah, Nevada's in here. And most of California is out in the ocean, and it hasn't formed yet. So we take these various components that made up the Cretaceous of Western North America. The component that we call the Magmatic Arc, magmatic from the word magma, which means molten rock. So the Magmatic Arc forms up through, there's the Nevada-California border for reference there. So you can see the volcanoes along here. This part of it today becomes the Sierra Nevada. The part down here is the Peninsular Ranges, which of course are the mountains straight east of us today. So at one time, the Sierra Nevada and the Peninsular Ranges were all tied in with it turns out that this is one of the largest magmatic arcs in the entire geologic record. I mean, it is just super in scale. So I'm sure many of you have been to the Sierras and seen those huge masses of granite. You've been to Escondido and east from there and seen the huge masses of granite everywhere. Well, that formed by the subduction of this oceanic plate under Western North America. And between the arc and the trench was this basin that we call we name it the Great Valley sequence after the Great Valley or the Central Valley of California. And then the trench deposits we call the Franciscan after San Francisco. In fact, the type section for the place where the Franciscan was named is literally where I think it's the south pier of Golden Gate Bridge sits in rock. It sits in that Franciscan rock. That's where the name comes from. Then to the east was this Western Interior Seaway that covered much of the Four Corners area all the way down across Texas and all the way on up to Alaska. Okay, so let's look at a few terms here. I'm trying to limit the terms as much as I can, but it's pretty difficult not to use some of them. So let's look at a couple of diagrams here to try to understand then what was going on with Western North America when we had this normal subduction. So this is just sort of a general cartoon. This could be from any textbook, any geologic textbook out there, showing a typical subduction zone. The oceanic plate dips under the adjacent continental block or island arc, depending on several different things. And so this is the arc, or the magmatic arc. This is the basin between the arc and the ocean, and the trench that we call the forearc basin. And then this is the trench area through here. Now, if we make this more specific to the California situation, so now we're just going to modify this diagram slightly to make it more accurate as it applies to California. So here's the arc, the Sierra Nevada and the Peninsular Ranges. Here's the forearc basin, what's called the Great Valley. And then this is that huge wedge of material that forms in the trench and adjacent to the trench. It's called the Franciscan. Now, it doesn't take an awful lot of knowledge to realize that when one plate is going under another plate, there's got to be a lot of stress at that boundary. So things that are deposited, sediments that are deposited in this region, are being ripped up and shoved out of the way. And now, when I say this takes place over tens of millions of years, not as fast as I'm saying it, of course. So we build this huge wedge of these deep sea sediments that the new package comes in and it gets pushed over the older package, and again and again and again, and we get these packages of very complicated rock stacked up. If we look at more detail at this part of the diagram, in some places we're getting fairly normal sedimentary conditions where sediment is coming down a slope and being deposited along or near the trench. In other cases, we're getting situations where the rocks are being disturbed shortly after they're deposited, and they become what we call a mélange. Mélange is French for mixture. And so the rocks get all mixed up in this very complicated area right through here. There's some other points on here I don't have to go into for this talk, so we'll just move on. Okay. These are pictures of this Franciscan. Most of these are from the Central Coast. The lower right, this is part of the Big Sur Coast. If you haven't been there, you better get there. It's just an unbelievable area. I understand the road's open again, I think. That's what I heard. It was closed for almost 2 years because one of these blocks of Franciscan came sliding down and covered the highway. So you look at a rock like this, it's very difficult to see bedding. Oh, you see something here, but you can't trace it anywhere. You see something here, but it goes into something. It just looks chaotic. It doesn't look like normal bedding that we might see in a lot of sedimentary rocks. So hence the term melange. This is a close-up of the melange, and this is right at right below the Hearst Castle, right along the coast. Beautiful coastal area there. Maybe you know where the Elephant Seal viewing area is. This was just a mile or so from, if you're familiar with that part of the world. So this is the melange here, and lo and behold, there's a chunk. And there's no doubt that this chunk is embedded in this melange. But this chunk is a piece of oceanic rock. It's a piece of oceanic crust. The term we use for this, when a piece of ocean crust gets embedded in continental deposits, we call it an ophiolite. So I meant to point that out on a previous screen so you could see it spelled, but anyway. So this is a block of oceanic crust that is literally brought in to this subduction zone with this mess of rock. These are pieces of serpentinized, these black rocks are serpentinite. Serpentinite, pure forms of it are jade and what's the other, there's another soapstone, and so forth. These are rocks that are mashed to oblivion, and they have chemical changes that turns them into these. They're very bluish in color, although maybe you can see it more in, I don't know, maybe some in there. That's actually a blue rock, but the way the sunlight's reflecting doesn't make it look very blue. And they're called blue schists. The only place in the geologic system where these rocks can form is in a subduction zone. Now, how do we know that? Because the minerals in here tell us that this rock formed at very, very high pressures, but very low temperatures. So it's unlikely that rock ever melted. But it was completely rearranged chemically by the high pressure. So when you think about a subduction zone, what's going down the subduction? Cold oceanic crust is going down in the subduction zone. So the temperatures are relatively cool compared to other places on Earth at the same depth. So if you drilled a hole off Japan today in the trench there and down into the crust, you would find that temperatures were much cooler than at the same depths as if you went under the center of Japan and drilled down to the same depth. It would be much warmer. So because of the cool, relatively, again, I mean, it's still hotter than hell, but relatively speaking, it's cool. And so the minerals that form are these blue minerals that give this rock its characteristic, and hence we call it a blue schist. So the only place it can form is in a subduction zone. This also formed in the subduction zone, the top rock here, but an interesting thing happened here. For some reason that we don't completely understand, this part of the subduction zone just sat there. It just sat there and received sediment, and it was preserved. That's very unusual. Usually the subduction zones are just hammered. Well, this particular area, we can clearly see the bedding. If we were up close, we'd see the cross bedding in here and so forth. It's probably not an exaggeration to say that those sediments formed at 20,000 feet of water depth in a trench. That's about the average depth of trenches today, give or take. Deepest one is what, 31,000 or something like that in the Marianas Trench. So here's a trench deposit perfectly preserved. This is at the little town of Cambria. If you know where that is, about almost exactly halfway up the coast. Then the other thing we see in these Franciscan rocks are, if you look at these, it's not hard to imagine pillows, is it? Looks like a kind of a pillow shape. They're all over the place in here. They're mostly the same size, but they vary a little bit. Well, this is a pillow lava, we call it. The composition of this rock, it's a lava, it's a basaltic lava. And it formed underwater. And how do we know that? Because when lava flows underwater, pillows form on top of it. If you go scuba diving where the volcano's going into the Pacific off Hawaii right now, you would literally see pillow lavas form as well as being boiled like a lobster in a pot. Anyway, so you can actually see these forming today. So again, we're using the present as the key to the past, aren't we, to understand some of these processes. And then finally we get to the forearc. Well, we're sitting, well, not quite here, 5 miles west. You're on the forearc deposits. The upper shot is the Sunset Cliffs, and the lower shot, of course, is Point Loma. These are Cretaceous Turbidites. Turbidites, have you heard that term? Okay, so we get a mixture of sediment up in shallow water that piles up over tens of thousands of years, and along comes some kind of an event, a big earthquake, a huge storm, and it takes this sediment and picks it up, moves it to the edge of the shallow water, and sends it down into deep water. So it's a slurry of water and sediment mixed together. And as it flows down the slope into the depths of the ocean, the coarsest material settles out first. Makes sense, right? The coarsest sands are going to settle out first, and gravels, and then the fine material settles out later. So if we look at this, each one of these layers of sand is the base of a turbidite. Now they're not all the same thickness, but they're pretty rhythmic. Bang, 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 bang. And then the recesses between are the muds. And you could go to Sunset Cliffs and you could actually count these if you wish. I'm sure some geologists have done that. But anyway, so these are examples of turbidites. So these form between the arc and the trench in the four-arc basin. And so that's the part we see right here. In fact, we can actually see all three of those parts in San Diego, and we have to go up into Orange County to see one of them. We've got the four-arc deposits. We certainly had the Magmatic Arc deposits to the east of us. Escondido basically sits on all granite. If you've been to the Wild Animal Park, that's all granite mounds that the animals are patrolling out there. To see the Franciscan, you have to go, the closest place to see it is Catalina Island. So that's not too far away. So all three of those components are in Southern California. Okay, so moving through the end, as we move towards the middle and end of the Cretaceous, a very interesting thing happens that's going to change the nature of our boundary that I've been talking about. And that is a thickened slab of oceanic crust, what we call an oceanic plateau. Do we have these today? We have bunches of them today. The biggest one in the world is the Ontauk Java Plateau, which is, as I speak, is colliding with the very edge of Australia. There's a great big one off of Antarctica called the, I can never pronounce it, Kerguelen Plateau. These are in water depths of several thousands of feet, but instead of being at the level of the abyssal plain, so the abyssal plain averages 12 to 15,000 feet depth, right? Okay, these oceanic plateaus, the depth over them might only be 2,000 or 3,000 feet of water. So what is happening there is for one reason or another, the oceanic crust is thicker under these plateaus than in other parts of the ocean. So here's a so-called normal subduction zone, and it's kind of like throwing a lawnmower in a tree stripping machine. You know, those things that take care of the trees, throwing a lawnmower in there. It would wreak havoc. And that's what happened here when this very thick oceanic crust collided with Western North America at about 80, 84, 85 million years ago. The subduction zone immediately responded to this, and again, immediately in geologic terms. It responded to this. So, here's normal subduction, 45-degree angle, give or take, okay? So this is early and middle Cretaceous. Towards the end of the Cretaceous into the Cenozoic, the angle is much shallower, perhaps around 20 degrees. And this thickened slab is sliding down the throat of the subduction zone until later in the Cenozoic, it ends up under what is today the Colorado Plateau. So this thing today is actually even further east than that. In fact, some geologists think it's almost as far east as the Appalachians. Because these things that subduct under continents, they keep going for a long time and long distances. So look at here, okay? So here's this thickened slab, and it's going down, and here it is, let's say 30 million years after this picture, okay? So plus 30 million years, it's under here. Well, this is just really goofing things up because the depth of the subducted plate under what was the Sierra Nevada is now too shallow to cause the arc to be active. it doesn't get hot enough because the crust doesn't go deep enough. See here, when we reach a certain depth, it triggers a melting in this region, and that melting causes these plutons, these igneous rocks, to rise and form the arc. But here we don't have enough depth. So the subduction continues, and finally, under what is today the Rocky Mountains and Colorado Plateau, things start to melt, and we get magma way east of where the normal arc is. You might say, well, how do we know this? I mean, this sounds pretty far-fetched. Once again, it's happening today in the Andes. Okay, if you look at the Andes Mountains, you can follow them along, and they're a fairly narrow mountain range. I should have put a map up of that. A fairly narrow mountain range coming from Colombia and going on down the coast. All of a sudden, they quintuple in width. And that's where shallow subduction is occurring today. How do we know that? We can look at it seismically and see the record of that slab that is subducted under the Andes at a shallow angle. So there's an example today of what we think was going on through the late Cretaceous and the Cenozoic, early part of the Cenozoic in Western North America. So again, we have a present helping us understand the past. Okay, so now we are starting to change things. Now, don't make the mistake of thinking subduction ended. The subduction didn't stop. Its nature changed. It's still subduction. We still have the trench. We still have the Franciscan being formed out here. It's just that there is no arc here anymore because the arc is about to shift much further east. And here we can see it at about 65 million years ago, which, oh, by the way, is when the meteor hit that killed the dinosaurs or whatever. Well, that's another topic. So here's the trench. And here, this is the San Juan volcanic field, San Juan Mountains of southwestern Colorado. It's full of volcanic rocks. The oldest volcanic rocks there are about 60 million years old. Maybe a little younger, but in that range. Okay, we all used to drink Coors beer. I know it's out of, now with all the San Diego beers. If you look at the Coors can, there's a mesa on that can. That mesa is formed by this volcano right here. That's where the arc is about 65 to 60 million years ago. Look at that distance. 1,500 miles. It should be here with normal subduction, but with shallow subduction, it's way the heck out here. These arcs in southwestern New Mexico, I've seen some of these volcanoes and some of these in eastern Arizona. So the arc is way the heck out here. So, what I'm going to do now is very quickly, because the details bog down very easily here, I'm going to take you through a series of these simplified paleogeographic maps to show what is going to happen following this shallow subduction, okay? So, the first thing is this East Pacific rise, which is shown by this jagged blue line, is going to move closer and closer, and finally it intercepts Western North America at about 31, 32 million years ago. This is at 24, so after that has happened a little bit. Okay, here's what you have to understand. This is one of the more complicated things in geology, but I think I can explain it in such a way that it makes sense. Okay, the Farallon plate, which is this plate up here, is moving more or less eastward at a pretty rapid rate, and it's subducting under Western North America. So let's give it a fairly long arrow. The arrow will represent its speed relative to other arrows on the map, okay? A vector, all right? The Pacific plate, which is the other side of the East Pacific rise, so it's moving away from the rise, is moving to the west-northwest. And it is presently the fastest moving plate on Earth. And it probably back 24 million years ago was also the fastest moving plate on Earth. Meanwhile, North America, which is separating from Europe during all this time, right? Well, the Atlantic Ocean slows down about 50 million or so years ago, 60 million years ago. And so the vectors for the motion of North America are much smaller because the Atlantic is not spreading as rapidly anymore. So we give these small vectors, okay? So North America is moving this way. The Farallon plate is subducting. We still have the arc up here. Here's the Cascade Arc up here from Northern California on up into Oregon and Washington. So normal subduction here, but look at the geometry here. It's totally different. This plate is moving away from the East Pacific Rise, which is now jammed up against Western North America, and it is moving at a speed 3 to 5 to 6 times faster than North America is moving. That doesn't seem possible, does it? How can one plate pull away from another plate? Well, North America is a continent. Continents are very thick crust. So what's happening is as the Pacific plate is pulling away, the thick crust of North America is extending, much like a piece of taffy. So the Pacific plate is pulling Western North America apart. And so as you pull a piece of taffy or a piece of chewing gum apart, it thins or it necks, doesn't it? So that's what starts to happen to Western North America. And it starts breaking up into all these basins and fault zones and so forth as the crust pulls away and thins. Does that make at least some sense? So I keep these arrows on here for the ensuing maps. By 18 million years, we've got a pretty long boundary between the Pacific plate and North America. And one of these blocks in here, that today we call the Western Transverse Range, decided to sort of stick to the Pacific plate rather than slide along with it. It sort of stuck to it. And what it does over a period of time, look at its orientation here, its orientation here, its orientation here, its orientation here. It is literally swinging away from North America. Well, at one time, let's go back to where it's almost in place, okay? I've got my pointer exactly where San Diego was then. And right here, I've got my pointer exactly where Santa Barbara was then. So Santa Barbara was a suburb of San Diego. Literally. I mean, there's no doubt about that. This is very, very well known. So as this plate starts to pull apart, this Western Transverse Range starts to rotate, the crust behind it is being chopped up like crazy. Now, you can't carve a hole, you can't pull the crust apart down to the mantle. The Earth just won't let that happen. But the crust will thin quite dramatically, and in some areas it will pop up. And that's what we call the California Borderlands. That's what's underwater for 100 to 150 miles offshore. And if we drain that, was it Nat Geo that drains the oceans? Somebody drains the oceans. If we drained that, we would see a terrain out there very much like what we see along parts of the coast today. Uplands and valleys and so forth. We'd see high spots and low spots. 120 miles off the coast of San Diego is a place called the Cortes Banks. It's a famous area for skin diving, and they're trying to make a national park out of it. The Cortes Banks are 30 feet underwater? I'm not sure. They're pretty shallow, 100 and some miles offshore. So it's one of these high areas. An even higher area is Santa Catalina Island. It sticks up 1,300 feet high. It's a big, tall mountain range that popped up off the coast here. So this change now to this new type of margin is completely changing the boundary. And now finally we get towards the present here, and the Western Transverse Ranges are oriented east-west. Why are they called the Transverse Ranges? Because they're transverse to every other mountain range in California. They run basically east-west. The other mountain ranges run north-northwest, south-southeast, right? Mostly. There's a little variation, but. So anyway, all this complicated shoreline we see today is brought about, is related to these changes. So now what I'm going to do, we're going to go through a series of paleogeographic maps now, just following these events through time. So we start at 60, normal subduction. At 50 million years, there's a town just east of here called Poway. Poway sits on at least part of it sits on a broad, flat area that's underlain by a series of conglomerates and gravels that are bird egg size to, I think, even basketball size, some of the bigger clasts. And when geologists first saw this conglomerate, let's call it a conglomerate, when geologists first saw that, they were puzzled because the components that make up that conglomerate didn't look like any other rock in Southern California. Nothing. Nothing like what's in the Peninsular Ranges, nothing like what's in the Sierras, just totally different. Well, a fellow at San Diego State, who I understand is giving the talk here next week, Pat Abbott, he started tracing those clasts back to the east, along with some other geologists, and they finally found the source of this Poway conglomerate right about almost in Mexico, but almost into Arizona, right about at the bend where the Arizona line makes this bend right here. So right in here are the rocks that are the source of the Poway conglomerate. So that means a river had to cut across all the way through the Peninsular Ranges here, drain into the Pacific Ocean, and make this huge complex of gravels and further off sands and muds that we call the Poway group. It goes by different names, but let's just call it the Poway group for here. And we can see this. We can see these rocks at Torrey Pines. If you take the coaster where it cuts along through that valley there near Sorrento Valley, you can see outcrops of it there, and you can trace it all the way down and well down into Sonora, Mexico. So a very interesting unit that probably San Diego's most famous geologic unit, this Poway. Okay, moving right along, here comes the East Pacific Rise. We jam up the subduction zone. Now, this plate is pulling on these rocks, and things are pulling apart. And this continues into the Miocene. Look at all these individual little basins in through here. And these are pretty accurate. I use some very good geologic information to plot these various basins on these maps. Right in through here. And here's the transverse range starting to rotate. Here it's rotating a little further. Again, look at these individual basins through here. And in these basins is deposited probably California's most famous geologic unit, the Monterey Formation, named after Monterey, or Monterey Peninsula. And it's a series of these turbidites. You can see, again, the alternate bedding of finer and coarser deposits that were deposited in these various basins. And one thing about the Monterey, if you look at 50 outcrops of the Monterey, you're going to see 50 different varieties of the Monterey. It's different almost every place you look at it, but it still has a consistency. But there's enough of a difference that we can see these differences from place to place. And so we can restore these basins based on the details of the Monterey Formation. We can tell which direction the sediment came from, how deep the water was, what the chemistry of the water was, what the temperature of the water was. There are actually thermal maps of the Monterey Formation as to what the water temperature was across the whole thing. This is, of course, is something the oil geologists want to know, because the Monterey Formation has probably yielded more oil than any other single geologic unit on Earth, and that includes the Middle East. So, now, I'm not saying the Middle East produces far more oil. There's another interesting unit here. I'm just going to briefly touch on this. This gets a little bit more complicated. Remember I said as we pull the crust apart, some pieces drop down, some pieces pop up. Well, off the coast of Orange County, a major island mountain range popped up, and it shed a series of conglomerates eastward. Well, normally when you look at a coastline, you expect the sediments to go from the coast to the ocean, right? These deposits go the opposite way. If you've been to Dana Point, you've seen these deposits. And I know you probably can't see it real well in this photograph, but I'll guarantee you that you can actually walk along the shoreline here, and you can actually see the larger particles here getting finer as you move in this direction. You can actually see that walking along that short distance of the coast. So that's telling us that whatever shed this debris was pretty darn close. A mile or two away? You might say, well, where is it now? Who knows? I mean, it's been faulted away. It could have been a piece of Santa Catalina Island, but it probably isn't quite that simple. So anyway, this contains pieces of the Catalina schist. There's no doubt where it came from islands like Catalina Island. I'm not saying it was Catalina Island, but islands like it. This is at Laguna Beach, and the sands here have pebbles of this stuff in it and so forth. So, all right, finally we're winding down here, and I want to do one more quick thing as we finish off here with the paleogeography. The ice ages, a close-up of the lakes and the ice ages of the Southwest. And rather than read all this summary to you, I know it's getting a little late here, what I want to do is I want to run through these same maps really quickly here, and you can actually watch the continent expand to the southwest, and then eventually watch blocks from here move up that way. So two things to watch for: things moving this way and things moving that way. Okay, one more time. See the extension of the basin and range? So that's why that one series of maps I showed you, those Palin spastic maps, are so important. That's how I can do that. I can follow the details of that. Well, I've kept you long enough, and probably given more detail than you need, but to me this area of California is one of the most exciting areas geologically on Earth. And if you're really interested in geology, go out and explore these places. Dana Point's not far away. Right next to the Dana Point is a world-class submarine fan deposit that was literally deposited in about 2 miles of ocean depth from a shoreline that was probably less than a mile away. So that's a pretty steep shoreline. And that's a deep sea fan deposit. If you know where San Clemente State Beach or State Park is, when you walk the trail down there, you walk right through that fan. Or if you go to Dana Point, you see another branch of it. You got all the granites to the east of us. It's not all granite, of course. Those of you that know that country know that there's other rock types than granites. There's basalts, and there's rhyolites, and there's other volcanics and so forth. So it's really a neat place to look at rocks. So anyway, I encourage you to do that. Thanks for your attention.